Probability and math statistics, we'll be studying weak law of large numbers. But before we start, we need some basic definitions of few things. Like, first of all, we must know what is probability density function. In short, we say PDF. So it is any function f defined from set of reals to positive reals. This is said to be probability density function. If it satisfies these two conditions, first of all, function is positive, or rather I should say non-negative, for all x belongs to reals. And secondly, the integration from minus infinity to infinity is 1. These two criteria must be satisfied by the function to be a probability density function. Next, we need some various measures of central tendency. Let x be a random variable with density function then mean of x, which is denoted by mu x or expectation of x, is defined as we generally write x in square bracket minus infinity to infinity x fx. This is for x being continuous random variable, and similarly, if we are finding expectation of x square, then in the formula we'll be writing x square in place of x. Rest is same. And in a similar way, if we are talking about discrete random variable, integration will get converted into summation. Otherwise, it is in the form of integration if we are in continuous random variable. Next is variance. Variance of random variable x, denoted as sigma square or var x, and is defined as minus infinity to infinity. See, in expectation we write x, and in variance we write x minus mean square fx dx. This is a kind of formula which we need to remember, though we have proofs for them also, but right now we need to remember this for other theorems and questions. So this is the deviation about mean. Every term, every observation will be deviated by the mean, taking square of this with the PDF function, and then the integration is minus infinity to infinity. The formula is for x being continuous random variable. The similar formula will be there for discrete random variable. In place of integration we'll be writing summation. Here mu x is mean of x, right? We can solve this further to simplify. Opening the square, x square minus 2x mu x plus mu x square simplifying integration in three parts, x square fx, and here mu x and 2 is constant. Once found, mean will be fixed, a constant quantity. Running one is x is running. Same, mu x square is a fixed quantity. Mu x square I need to write outside the integral. So this is nothing but expectation of x square, and this is another definition of mu x or expectation of x, and this is simply 1. By the definition of PDF we have written this minus infinity to infinity integration of f is 1. So simplifying, so this is minus mu x square, which is nothing but square of expectation. Square of expectation. So that is the connection between variance and mean, right? So now coming back to the main topic, weak law of large numbers, and the very first one is Markov's inequality. Which states that if x is a non-negative random variable, then for any a positive, probability of random variable x greater than equals to a is less than equals to expectation of x divided by a. See, whichever constant is placed here, suppose if we are finding probability of x greater than equals to 3, so 3 will be appearing here with this inequality with expectation of the same variable. So proof of this is, let x be the continuous random variable. See, we are proving the result for continuous random variable. Same result can be proved for a discrete random variable. With probability density function fx. For simplicity, we sometimes write this as simple fx also. It is understood when we are talking in some specific random variable, so it is fixed here. Now finding expectation as per the formula, minus infinity to infinity x fx. And since x cannot take negative values because it is non-negative random variable, So our integration will reduce to 0 to infinity. And for simplicity we are writing simple fx. So this is breakable as, suppose a is the breaking point, because we need to find the probability at the breaking point of a. So we will be breaking the integral 0 to a plus a to infinity, the same integral. And this can be written as greater than equals to a to infinity x fx. And this is greater than equals to if x is replaceable by a. Is it clear? See, here this was sum of two quantities. So if I remove this, which is a positive quantity because x is non-negative, a is positive, so this is a positive quantity. So whatever the sum is, it will be greater than or equals to this value. If we are replacing two values with one, we will be replacing the equality by this inequality greater than equals to. And now this is running for each and every value of x. I am fixing the value of x as a. So this is one of the value of this integral, and this contains more values. So this statement will be greater than equals to a particular value of the integral. When I fixed x as a, because x can take many values, I am fixing it for one particular value. Integration is same. So this contains more than this value, that's why this is greater than equals to this. And now solving this, a will be taken outside. We are left with a to infinity, and which is nothing but the probability of random variable x greater than equals to a, because integration is moving from a to infinity. So we are finding by this integral what we are finding probability of random variable x greater than equals to a when the value starts from a onwards. And now by this we have expectation greater than equals to this value. Shifting a over here, we get the result. So this one is simple Markov's inequality. We have generalized form also, where in place of x we have function, a function which is also based on continuous random variable, and the function is also non-negative function. So we'll be doing the same inequality with that generalized form. Generalized Markov's inequality. If x be a random variable, and g be a non-negative function, with R as domain, then the theorem states probability of g of x greater than equals to a specific number k less than equals to expectation of g of x divided by k for every k positive. So in place of random variable x, we have a function of random variable. Criteria is same. Let x be a continuous random variable. so that we can prove the result in terms of integration with probability density function. Then by definition of expectation, it is like this. And since g is a non-negative function too, x is also, see, x here is random variable, it is not mentioned here. The x is taking only non-negative values, so that's why the thing will run from minus infinity to infinity. And this will be breakdown as two sets, set A and set B, where the breakdown of sets is with a parameter k. Like A contains those values of random variable on which the function takes value greater than equals to k, because we need to find probability on this. So that is the breaking point. Here the value of the function is less than k. Since we are interested in this only, so we'll be removing this and applying the greater symbol, because both are positive quantities since g is non-negative function. So this is greater than equals to A, because this is positive quantity. So whatever value it takes, the sum will be greater than this value, right? Now simplifying this, this is further greater than equals to, if I replace gx as k, the integration remains. Why? Because k is the least value. So I'm replacing the function with the least value, hence the integration will be greater than equals to. The reason is value of the function is greater than equals to k for all elements in this set. And now solving this, k will appear outside and we are left with integration, this only, which is nothing but the probability of the function where gx is greater than equals to k. Why? Because A is a kind of set where the value of the function is greater than equals to k. That's why this integration is providing us the probability where g of x is the random variable on random variable x takes value greater than equals to k. So that is why this is convertible as probability. So now just having this value with a greater symbol, with this we arrive at the conclusion. Shifting k over here, with a greater symbol, we are left with this probability. Result is proved. In this we have a corollary also where the function takes value less than k. So when we need to find probability of random variable taking value less than k, that is replaceable with the greater than symbol and 1 minus this. So we need to prove that corollary also. In this we have probability of g of x less than k is greater than equals to 1 minus expectation of g of x upon k. So in general, the probability function takes value like this: g of x greater than equals to k plus probability of g of x less than k. Together the sum is 1, and we have found this value. So this is 1 minus probability of this. See, since we have retrieved this value as less than symbol, with less than symbol, by taking negative sign this will get converted into greater than symbol. As p of g of x is less than equals to expectation of g of x upon k, so the negative of this value will be greater than equals to negative of this. So this is replaceable with greater than equals to 1 minus expectation of g of x upon k, right? So we need to remember this also as a result. So the next inequality is Chebyshev inequality. Well, the pronunciation of this name is totally Indian right now, what I said, but basically this one is the name of a Russian. So this is a Russian name, and in Russia it is pronounced as Chebyshev. So we say here Chebyshev inequality. What it says, the let x be a random variable with expectation and variance given. Expectation as mu, variance as sigma square. Then for any constant c, C positive, the probability of x minus mu modulus greater than equals to C will be less than equals to sigma square upon C square. Whatever boundary is here, C square, that constant square will be present here with this less than quantity, or the reverse condition, less than C will be greater than equals to 1 minus. Similar kind of situation which we have studied just now in corollary, right? So this is totally another generalization of Markov's. Since we are using that by Markov's inequality, we have already proved the result that we have proved this result by Markov's, that if we have probability of random variable x based on a constant greater than equals to k, it will be less than symbol expectation of that random variable divided by that constant. So using that, instead of x, I'm having x minus mu square, and instead of k I'm having c square. So this will be replaceable with expect less than equal to expectation of x minus mu square and divided by the same constant c square, right? And this is nothing but sigma square, the variance. So I'm replacing this square with the modulus by the inequality. Whenever we have a square concept, we replace it with the modulus concept with the positive quantities only. So here the square is replaceable with modulus of x minus mu greater than equals to c. The complete square has been replaced with a positive quantity and c here given as c positive, and x square will be replaceable with modulus of x, so this way, and this is now replaceable with sigma square by c square, which proves this part, right? And this is quite obvious by taking their sum as equal to 1, like the corollary based. This is general concept of probability, that overall sum goes to 1. And to find this, so this will be negative here, and in negative of a quantity the signs get reversed, with less than symbol get reversed as greater than, and the value get the negative sign. So this proves the second part. Now we have different writing exemptions for this, like in modulus. When we deal in modulus x less than k, that simply means x lying between minus k to k. So in a similar way I can see this quantity as minus c to c x minus mu, and we get the same result. These results are used to do questions. So if you are interested in doing questions based on these inequalities, do let me know. I'll make a video on that too.